Hello everybody, and hello people out on the internet and on the satellite links and wherever else we have here. So as it says here, my name is Peter Keenan from University College Dublin, and for those of you that haven't been in Dublin, this is our campus, and we are the largest university in Ireland with 24,000 students, and we've been around since 1854, so gotten the, I suppose we're reasonably experienced in this university business. The business school, with which I'm part of, has been around only since 1908, when we had 3 students. Now we have 3,000 students, so that's significant growth over that period. And the building you see on the slide is is where the postgraduates, which is in a separate campus. So we're hoping to have Angel visit us in the summertime, so you can see his place of residence there on the thing. So of those postgraduates, we run courses in business analytics. So I'll give you, I suppose, some of the background to our department. The department was founded in the late 70s, and we started the Master of Management Science degree in 1978, which so it's around that time the department was founded. Our first professor, Harry Harrison, won the Franz Edelman Award, which, as you're possibly aware, is the Operations Research Award for the best practical or corporate implementation, if you like, of management science. And he was concerned with routing of drugs to pharmacies and people. Now, probably you look back at his example, it was quite a small one compared to the kinds of things that win that prize today, but at that time it was nevertheless at the leading edge of operations research. So following that period of time, the type of work that we were doing, and I ended up doing my master's there and eventually doing a PhD, was there were a few different things. One was milk collection, which is kind of economically important in Ireland in the agricultural business. And milk collection as a routing problem has a few different, first of all, it's a collection problem, which is slightly different from the typical problems which are delivery. It's on tankers, so the actual quantities are, there's a capacity and a certain number of litres or whatever within that, and it's a problem whose volumes change significantly throughout the year. So in the milk business, at this time of year, the volumes begin to increase very substantially because the grass begins to grow and so on, so that the actual routing is seasonal in that sense. And it's something which we did work on that, back in those days, using the IBM VSPX software, which implements Clark-Wright algorithm, which was state of the art, I suppose, at the time. But this is an area of routing which has continues to be important, but also the thing that has changed, and the thing that has changed in every aspect of analytics, if you like, is the availability of data. So back in those days, there were no digital maps. You had to digitize your own map, which usually meant that was about the cost, and you didn't really go to too much. The quality of the map that you digitize yourself was limited to some extent. Nowadays, of course, not only do we have digitized maps, but things like milk collection has onboard computing devices that record the quality of the milk and the temperature of the milk and so on at the time when it's collected. So there's a huge amount of data in that kind of area that wasn't available to us at that time. The other problem we had was postal delivery, which we'll come back to that in a second, I suppose, which was something I worked on myself. We had problems like courier routing, so collecting checks from banks, which I suppose is another type of problem, that people were writing paper checks which had to be brought to a centralized depot overnight for processing and posting to bank accounts. So that was a problem where you had to basically collect from the bank branches after the time of closure at 5 p.m. whatever, and try and get all the checks processed before morning, so that it was a combination of a scheduling problem at the depot and an actual routing problem to get the volumes transported, so that you could do them in the time available. So that kind of problem. We also did some location analysis for the banks at that time. Now, they didn't actually, I think, fully follow our suggestions, in that we said, well, if you build a new place here, this can actually be more optimal. They probably continued with their existing centres, but it was an interesting project all the same. I suppose there was a difference as well with the dealing with these companies. Banks are much more focused on their job than the post office is, because it's a kind of government organisation, and it's a little bit sort of in terms of getting data and so on. There's a huge difference in the banks are much more focused on getting the job done. The post office didn't even know, for example, how long it took to deliver a letter. They hadn't actually studied that in any great depth. So they had ways of doing it, but they had never actually broken it down into any sort of data. We did things like harbour optimization, so you have a container port where the containers have to go out on ships, and but they have to be sequenced in some way for loading purposes and moved around a little bit. So there's a ship leaving today for one place and a ship leaving next week for somewhere else. Both containers arrive today from a truck. One has to be put to one side and it has to be left until next week. And that kind of problem was the kind of things we were doing. So more recently then, in terms of our own department, we redesignated ourselves analytics rather than management science, which is as much a marketing thing as anything else, because of course our real concern is with the quantitative use of techniques in business, or quantitative techniques in business. In a sense, we didn't have a limited view of that, but the term which we felt was closest to that nowadays is business analytics. So we retitled our master's degree Business Analytics, and we've now launched a BSc in Business Analytics, which started last year, which still has to achieve critical mass. It's not that well known at this stage. So the kinds of things going on in the department at the moment, with some work on decision making. So I think Angela's met my colleague Cathal Brewer, who has been working with multi-criteria decision making, and he's also been developing a theory of decision making, which is quite philosophical and is based in part on the work of a 13th century scholar in Barcelona, a guy called Lul. So we go far back in our literature search on these kinds of problems. I hope you're equally diligent in your PhDs and so on. And GIS, which is my own work, which I talk about. And we also have a centre of natural computing. So natural computing is the techniques such as genetic algorithms, and in particular, this group have developed genetic programming, which is an extension of that area of things. But and my colleagues, you'll see the book that they've written here, which is natural computing algorithms. So there's a lot of work being done on different kinds of things drawn from nature. We're all familiar with kind of ant algorithms, but there's things drawn from bees and zebras and whatever else. All manners of creatures are used to inspire algorithms. So there's a lot of work on this. And my colleague Paula Carroll then is working on telecommunication networks, which has obviously sort of optimization possibilities as well. So my own work was coming from the postal routing part of this research, and the problem we had, the work that was needed was that of rural postal routing. So in the post office in Ireland, Ireland has a particularly dispersed population, much more so than the majority of countries where people tend to live in villages and towns. For historical reasons, a lot of people in Ireland live distributed throughout the countryside. So these people need to get their letters, and they do receive letters every day, so there's not a post box situation or whatever which exists in some countries. So the post office have to have a van which goes around and delivers all of these letters, which is a significant cost for them. So there's a significant business problem as to how to do this. And so they came to us seeking help on this particular issue. So we did some work with them over time in addressing this problem. So this was a distinctive kind of problem because I characterize as the time-capacitated arc routing problem. So arc routing problems are where the demand is distributed on arcs. So obviously in the case of postal delivery, demand is in fact individual houses, which are points in one sense, but when you have a number of houses along a single street or a single road, and you must visit at least one of those, then you must pass along that road. So it's more realistic to characterize it as an arc routing problem than because of the high proportion of points to be visited. So when you have a delivery problem like delivering to shops or something, these things are relatively far apart. But when you're delivering things to houses, we have to deliver everything to a house. So for example, in Ireland at present, we have a census every 5 years. Every European country has one every 10 years, but we have one every 5 years. So the census forms are now being delivered to every house. That's essentially, although the houses are individual points, it's more useful to think of entire streets being delivered all at one time, which characterizes it as an arc routing problem. But it's an arc routing problem in the case of post delivery or indeed census forms and so on, where there's no actual volume limit as such. A van carrying post has no limit on the number it can carry. There's no size of a letter as such that a van is not full. A postman on foot has a volume capacity limit. A postman on a van has no such limit. So the only limit is the working day of the individual who's doing the work. So therefore the limit is a time limit and not a volume one. But that particular problem is one in which when you're driving around, time is used up not only by driving and stopping at houses, but even when you're making part of the journey, just going back to the depot or something when you're not actually doing anything. It's all part of your working day. So it is a question of minimizing the distance you travel, but it's a slightly different problem than the traditional problem. Now, I'm not going to talk too much about this, but that problem has been generalized in a recent paper, which is looking at deadheading demand, i.e. arc routing, where not only the service of particular locations uses up the resource, but also in part to use the resource when you're travelling along sections of road where you're not actually delivering at that point in time. But and we hope to do some work with you on this arc routing, but my talk today really is more concerned with GIS, because one of the things at that time when we started doing this work, once again, we didn't have a digitized database of road networks to do the work on, so we basically had to build our own, and that was, we had 6 or 7 people doing that work at one stage, but the quality of work, there was some limitations in terms of the actual maps and things were not quite up to date, so we were getting errors in the road database that we'd built, and those errors were compromising the acceptance of our work, because if we produce a route, perhaps an optimized route, whatever, if the route is actually based on bad data, it's not actually going to be acceptable, regardless of how optimal it actually is. So, but at that time, then the building of road databases by the GIS and so on this would have been mid-90s, had begun to take off. So in fact, we were in a situation where we started building our own road database, but before the project was finished, that was obsolete because the actual centralized mapping agency had started building a road database themselves. So we essentially built a road database which was then discarded because there was a new GIS-based database becoming available. So as a consequence, I became interested in GIS as an actual medium for the integration of management science and GIS, and that GIS not only allowed you to display maps on the screen, which is something that many people were using it for, but the GIS community have a lot of sophisticated modelling of their own, and that modelling can be integrated with modelling from traditional management science operations research, and gives you a richer set of problems, but also allows you address a set of practical problems which cannot easily be addressed by either side alone. In any case, this was the ARC routing work which we were talking about earlier, and this is just one output from that. So the objective, these networks are characterized by being extremely sparse, and you have a lot of these cul-de-sac things along the way. So it's not a typical road network such as you might find in a city like Barcelona, or the classic sort of New York, Manhattan type of network. And so it did present certain distinct problems. Okay, when I became more interested in GIS, then I started looking at the connections between vehicle routing and GIS. Vehicle routing was already at that stage a well-established area, so this was taken from the Bowden and Golden paper in 1981, so as a classification of problems. So they said, well, you have location constraints, which are the obvious, the points at which you collect milk or you deliver post or whatever it might be. And then you have the vehicle constraints, so you have depots and you can have heterogeneous vehicle fleets, which we were talking about earlier, and different characteristics like that. And it seemed to me that the thing that was missing from this particular analysis was there wasn't any real concern for how you get from A to B. So there was an expectation that somehow these vehicles get to these locations, but there wasn't much interest in how they actually get there. Now, obviously, some early vehicle routing was conducted on a coordinate basis, so that they basically didn't take much interest in the detail of the road network. And of course, the reason why they didn't do that was because in the absence of digitized road networks, it was extremely difficult to get the data required to have a detailed road network. But with the advent of GIS databases, things like road width and traffic number of lanes, this kind of thing was now available. So it seemed to me that it was appropriate to add to these kind of issues some of the extra things that were involved with this. So I suggested that we should have additional path constraints, so that the path constraints might reflect a problem that there are many situations in which the way we should get there, so we were discussing earlier, you have situations where you're going uphill or downhill or whatever can affect the fuel consumption of a vehicle. And so the nature of the network and the time to travel given network segments, and also vehicle type limitations on network segments, because if you have a large truck, you can't necessarily go down every small road and small street. It may have to confine itself to the major parts of the road network, whereas if you have a motorbike courier, then they can go perhaps on every type of road, and they're not restricted to only important roads in that. And the point was, I suppose, that this data had now become available because of the advent of GIS databases. But the other point was, and perhaps the path constraints are interesting but not fundamental, is that the spatial data allows us model better the nature of demands at various locations, because in certain types of problem, the actual demand at a location is not. We have, for example, we have point locations which may be simply a surrogate for a region around that point. So if you have a bus stop, let's say, the bus stop is not a point of demand. The actual point of demand are the people living in the houses or whatever near the bus stop. The bus stop is merely, so they somehow walk to the bus stop and get on the bus, so that the real demand is coming from the houses and so on around, so that you can use sort of GIS data to then calculate the demand on the bus stop, and from that derive your route for the actual. So in a sense, it's a kind of location allocation, if you like, but one which the demand for the individual points is being determined by some algorithms relating to the area that and the location of demands can be points, arc, or polygons, which so points, arcs, and polygons represent the data sources in the GIS. So clearly we have points and arcs in the case of VRP and arc routing, but a polygon is a region which gives rise to a so I mean you can have problems. The generalized TSP is one where you have to visit a point in every. So let's say you want to visit. There is one in Ireland where you do a tour of Ireland, visiting all the counties in Ireland within a day or something, which is a record-breaking kind of thing to do. That's a case where you need to visit one point which is within a polygon, i.e. within a region. So there are other examples in which you want to make use of regions, and the idea of regions wasn't in the original kind of vehicle routing way of thinking, which we're dealing with either arcs or points. Okay, so we mentioned bus stops. So a bus stop is actually drawing its demand from the from the people around it. But clearly with bus stops, if you have a bus that stops every 200 meters, then it gets a certain demand. If you have a bus that stops every 400 meters, by and large it's still the same demand. It's just that there's more people going to each bus stop, so that the actual and so there are modelling possibilities which you could assess the time taken to stop the bus and the time taken for that additional stop vis-a-vis the additional service level provided by the distance people have to walk and so on. So these kind of things lead to a richer class of problem. Things like agriculture collection is a rather simplistic diagram, but if you have some type of agriculture which is on a plain, it's on a plain, it's in a field, it's in a forest, whatever, and you want to pick up the crop when the harvest time or something, then essentially you need to have a number of collection points. But the collection points are deriving the volumes from the region which they in turn serve, to which the crop is brought. So the tractors bring the goods to some point and the truck comes and picks it up. So a good example of this is in things like forestry, where forestry is a relatively important economic activity, but the forests are cut down only infrequently. So every 30 years or 40 years or whatever, you come along and you remove the forest in a sense, and so you have to pick up all the trees and take them away. So you can actually model that particular problem, and the forestry industry is one in which there's actually quite a lot of advanced optimization going on. Okay, so I was also interested in the idea of rich paths, where the path had a number of constraints on it other than, so the endpoints were almost a trivial part of the problem, if you like. So an example of this would be hazardous goods. So there is a lot of literature on hazardous goods transportation, which are subject to a lot of rules and regulations as to this is, carrying acids and gas and different products like that. So if you're carrying your hazardous goods, you might say, well, I don't want my truckload of inflammable materials driving past my local school, which mightn't be a good thing, but equally you want to keep it on the main road perhaps, where it's a wide road and not likely to have an accident. You might not want, well, you may wish to not pass by your school, you may wish to pass by some other facility. So let's say your hazardous waste, you might want it to not go by a school, but you might want it to go near a fire station, because if it happened to blow up, then the fire station would be nearby. Or you might want it not to go right past the hospital, because it might blow up all the people in the hospital, but you might want it to be near a hospital, so that if it did blow up, then the ambulances could come quite quickly to the scene of the disaster. So there are examples of this. You can imagine a scenario in which you have facilities like fire engines or dispatch, of ambulances or something, and you want to keep within that particular range of service. So one example I had was, which I think, there was an example in Greece where they had security routing, loads of money going to banks. So they had certain criteria about these money going to banks that they didn't want. They wanted to be near a police station, really. So if they could route the thing right past the police station, it was less likely to be stolen at the point when it was on the street where the police station was, and they didn't want it perhaps to be near some other bridge or something which might be a good place to steal money. So this was an example of that kind of thing. So in GIS, you can generate things like buffers. So a buffer is around a shape, isn't just an area. So if you have a line and you generate a buffer, it's just a wider line. Effectively, you can have a 500-meter zone on either side of a line or something like that. So that in turn can be used for routing purposes, in that you could say, well, within a certain amount of distance of my road. So in Ireland, even one of the milk routing applications we had was a farmer who lived within a buffer close to a road would actually be delivered, would be collected from a vehicle travelling on that road. And that's, but you could have similar kinds of things. But also you can generate buffers around irregular polygon shapes. So that could lead to another sort of problem. So let's say you have a sensitive installation, let's say it's an airport or it's a jail, and you don't want people coming up to who might want to break in, or might, a security issue arising. Then if you define a security zone around that by a buffer, then the buffer is a GIS concept, but that buffer can give you a set of arcs, so that you can, the roads which intersect with that buffer can give you a set of arcs, and then on that set of arcs you can generate an arc routing problem. So the arc routing problem then gives you a security patrol route by which you can visit every road near your airport to see are there any terrorists or whatever it might be hanging around in that particular area. So you're combining a mixture of sort of GIS, which is giving you the spatial area which you want to serve, with traditional arc routing or traditional VRP or whatever it might be, which is defining the means by which you are able to visit that area that you've now identified. And there's a variety of things that you think of where the GIS defines the region, but then within that region, what you're left with then is a relatively straightforward problem, but the interest in the problem arises from the combination of the two things. Neither bit is that difficult, but the combination is a useful one. Okay, so so this is the kind of the more elaborate end of GIS, if you like, which is surface lease cost. So in GIS, you can take a surface which has been mapped from satellites, whatever, and you can actually identify the least cost path, or the least cost. When I say path, the path implies that there's a direction along it. The set of points which represents a least cost surface, if you like. So, and then obviously that could present you with a routing possibility whereby you want to route along that particular path. So this kind of thing is used in GIS in all sorts of areas. So if you imagine that when people were building railways or something, 150 years ago, they had to have extensive surveys to find the best way to build a railway line. Now they can just get a satellite image and press a button and get the most level route will appear as a line on the map, which is a good deal less difficult to actually do. So people are using this kind of thing in GIS. Archaeologists and so on are looking for this data because people in historical times will have used the smoothest route, in a sense, which they would have worked out over centuries. So I even found a paper referring to an archaeologist who was examining the Roman aqueduct to Barcelona, and checking whether it was in fact following the most efficient route, which it was by and large. So the thing is, though, that this kind of thing, when combined with traditional management science, gives you interesting examples. But you often find, I mean, I've had 1 or 2 papers to review from the GIS where they were using this, but the kind of the routing part of what they were doing was a bit naive because they weren't really coming from that end of things. And likewise, in the management science area, people generally don't pay much attention to these kind of, because the combination of this kind of technique with traditional management science could lead to a lot of interesting stuff, which by and large the management science has a lot of management science is concerned with ever more refinements of TSP where everything's without any, which is fine, but the TSPs we have work pretty well. Sometimes there isn't the same interest in these newer problems that I think personally should exist. So what sort of things are we talking about here? Well, one example is military applications. Now, unfortunately, the military applications aren't always published for a variety of reasons. So you don't always get to hear about what the military people are doing. But think about it, travel on off-road vehicles is actually a very military thing to do, where you're driving your tank across, so that the military don't keep to roads in their battle simulations. They tend to go across the countryside. So the question is, when you are doing that, what do you want to do? Do you want to stay below the horizon and kind of sneak in, behind the other guys, or do you want to go up on top of the hill with your tank and shoot down into the valley? Either way, that these things can be modelled very effectively by a combination of GIS plus some kind of algorithm that's modelling the movement or the transportation aspect of things, and there's a lot of interesting examples of that. And of course, another thing which is analogous to a military application, which you mightn't necessarily think of, the thing that most people, the military application that most people get involved in is on the computer screen when they're playing one of these computer games or whatever, which I'm sure that you don't have time to do being PhD students. But in game development, these kind of techniques are used extensively to model the kind of tank warfare or whatever that's on computer games, and there's a variety of games and where you have these artificial landscapes, and they're using this kind of thing where there's interesting algorithms, which once again there is management science in there as well, which we but equally so other example I suppose is precision agriculture. So clearly, if you want to irrigate land, which isn't generally the case in Ireland, but might be the case in at least some parts of Spain, then you need to bring water to the particular places, but you want the exact amount of water delivered to be the minimum required in the case of irrigation. So the water required at a given location can be calculated by reference to the slope and the aspect, so it's south facing or whatever, and then from that data you could then work out a minimum algorithm, some kind of minimum network algorithm to actually deliver that minimum amount of water. So you have data from the GIS, if you like, on the precise amount of water needed, and then the operations research kind of approaches are graph algorithms that will allow you to deliver that amount of water. And having done so, you can then go back to your least cost surface to try and work out how to lay the pipe, so that they get the correct in a way that allows the correct fall to allow the water to flow and so on. So it's a combination of the two things. And then last example I have here, but you can possibly think of other ones. In fact, bonus prize for anyone who does think of another one, is the whole emergency evacuation kind of area of application, because a good example is a forest fire, because a forest fire, there is modelling for forest fires. that modelling takes into account things like the slope of the land and it takes into account the wind direction and so on. So it's quite a complex modelling. But if you're in a place with have had serious fires in places like Australia and California, then you have houses in the path of this fire. In what order do you evacuate the houses? So if you're running a government, fire service or something, then this becomes quite important. So obviously you can model the time at which the fire reaches a particular dwelling, but you also have to model the evacuation, because if the road that leading to that house has been cut off and you haven't evacuated the house, then you still have a problem. Even if the house hasn't yet been burned, you can't actually get up to it because the road that leads up to it is now within the fire zone. So you need to look at the network aspect of that. And if you want to evacuate a number of people, perhaps there's a logistics scheduling problem in how do you have a certain number of resources, how do you schedule that in order to evacuate people in a certain sequence. So that leads to a very rich problem which can be modelled, and it's a very, so there are similar ones with flood and so on, in the sense that flood is a little bit more predictable. Water tends to rise at a relatively predictable way, whereas forest fires are not entirely predictable, as the wind can change or something, and the actual, you need to recalculate things very quickly in that scenario. So, so really my point here is that we're familiar with traditional kind of algorithms which have tended to assume that the interesting bit is at the end. It's at the point, it's at the depot, it's at the place where the thing is picked up or it's delivered, and that there might well be some difference in the vehicle used. The vehicle might be large or small, or it might have a particular time constraint, or it might have a particular volume constraint. But my suggestion here is really that there is also an interesting set of problems where the topography of the landscape represents additional modelling capability, which we is largely now found in GIS, and is probably found in GIS journals rather than management science ones, but that there is a set of problems in between, which is an interesting one, and I think that people from sort of management science can take more interest in them and not leave them all to the GIS people. Okay, thank you.
Thank you. So we have time for some questions about, well, when you included these applications or OR and MS, Management Science purposes, together with GIS, so don't you think that maybe I miss here something applications to what we call smart cities? Because clearly to me it's one of the largest fields of applications, of potential applications. What do you think about that?
Well, clearly the bus stop example of that class of problem is very much central in smart cities kind of applications. So, I mean, the agriculture ones are a little bit different, but the notion that the public transport demand is derived to points, which are stations and bus stops and so on, but it's derived from the area around it. That's and the characteristics of that area is very much central to smart cities. And
but I am also thinking about I think new applications, like for instance, what about the traffic in the city? I mean, you could probably take decisions or help the traffic policy makers to take decisions based on the information you have about the current status of the traffic situation in the city, and then also on the available roads. And for instance, if you have to design or to decide about the waste collection management or the postal delivery, for instance, then you can try to decide about the best routes that in terms that they affect the less possible to the traffic situation, to the traffic congestion in a large city. So what do you think?
well, yeah. I mean, the postal collection not so much, because in cities postal collection's on foot and it doesn't affect the traffic. But things like street sweeping, and waste collection, these things need to be coordinated with the traffic, so that they're not trying to sweep the street in the rush hour, or at least on the side of the street which the traffic. So if traffic's going out one way and coming back in another time of the day, then sweep the street on the side that's quiet at that time of day. So there certainly is that, and waste collection. I mean, waste collection trucks do actually obstruct traffic as they stop, and that needs to be coordinated with the traffic flows. So I mean, that would be an obvious one. It still, though, is not quite. It's not using GIS in a rich way, though. It's more a management problem than an actual data problem. If the waste trucks were estimating demand somehow from the nature of the types of properties that were around or something, that would be more interesting.
Okay, another question I have for you is, well, as you say, the VRPs have been much more explored in the literature than the IRPs, the urban developments. So, which are, in your opinion, the main reasons to justify this? Do you have any idea why this is the case in the current literature?
Well, the problem is people. I mean, if you think of my former professor who got his prize back in 1979, I mean, he was delivering things to pharmacies, but that's the kind of problem that was economically important. So that's where people found it most useful to start trying to do work. So, and probably most problems are still more easily characterized as VRPs and point routing problems. So yeah, there's a lot of different applications for that. So there's probably a good reason to start on that problem first. People start the popular stuff that's most needed first, I suppose.
Also, I have the personal impression, or maybe this is wrong, but I want to share with you. I had the personal impression that some of the people who has been working more on the ARP, they mostly come from a more theoretical perspective than the people. I mean, by theoretical, I mean they are more like people from exact methods. I remember now some of the people at the University of Valencia who were professors of mine in the past when I studied there. So like Belenguer or Corberan itself, or there are several.
Yes, there's yeah.
Excellent researchers in that university, but they deal with these problems more from using only exact methods, or mainly exact methods. And it seems to me that only recently there are some researchers starting to apply more methodistics, more approximate methods to solve larger problems, larger instances. Is that impression correct, or do you think?
Well, I think that there's been a few different people. You're right that Valencia has been, has been doing a lot of work without necessarily. There's been a few different people have approached different subsets of the problem with different techniques, without, in some cases, without really giving a real. They solved their problem and they did a paper, and I'm not sure that they could attribute something that was taken up by a lot of other researchers. So in terms of the size of the problem, many of the problems that people deal with are not that large because of the nature of the problem they're working with. So if you have even something like waste collection, or if you go along a street with 100 houses on it, how many streets can you visit in the course of one trip? The vehicle fills up after a relatively small number of arcs. So therefore the problem is not very large in terms of the number of arcs. So my situation in the rural example was unusual because most examples are on city streets where there's a lot of people, or a significant number of people living. Even in Ireland, where you don't tend to have large apartment buildings, but houses, you can still easily visit 150 houses. So waste collection, the volumes begin to accumulate quite quickly in that context. And similarly, another example, snow clearance was one that was but that can also, volumes can accumulate quite quickly. So therefore, you don't have big problems in reality. The real problems are not are not very large in general.
Then another question for you is, which ones do you think are the emerging or the new challenges in the future of adulting problems, in your opinion?
I don't know that I have the answer to that. I mean, there are problems which people have seen, which perhaps they become aware of that they're addressing, which haven't been nobody else has felt the need to look at them because that problem is an unusual one. So I think if you think of the number of specializations of vehicle routing, then there are situations where any of those specializations probably has an equivalent in arc routing, and the majority of them haven't been looked at in any detail. So there's a variety of things there. As to which one is the one that represents the best example, I'm not sure of.
Like, for instance, the use of electric vehicles also in
Particularly, yeah, electric vehicles will be interesting for all problems. That's where we'll all be driving around in electric vehicles. Also, I think electric vehicles is the environmental, green is a big area of all kind of areas of application. So, not polluting things is actually quite important, and there will be many problems designed to because obviously, if the electric vehicle has an efficient route, then it not only does the electric vehicle not pollute, but it even doesn't pollute at the power station, which has to generate the power for the electric vehicle. So it's a green analytics. It was the flavour of the month.
Another question? No questions? Why? Okay, clear?
Which kind of software do you use for this?
Well, in the past, I used a GIS called Transcount, which was designed for transportation modelling, which has had the idea of routing networks and things built into it. Now, I haven't done much practical work in the last while. I mean, the situation with GIS products was GIS. I mean, if you think of mapping, the original idea of mapping was to produce a picture which people could, they could print out and look at. And so when GIS products, when digital databases and GIS products were designed, roughly that's what they were trying to do, was produce a picture. Now, we don't want a picture, we want a mathematical graph in which we can actually do things. So a lot of these GIS products weren't initially suited to doing this kind of work. So there's some papers in Lancaster University in Britain, they've done some examples, but I mean, if you spoken to them, they said it was really hard to do that because they were kind of trying to make the GIS do it. But since then, people like ArcGIS, which is the market leader, have actually added in network analysts, as an actual tool for doing this. So they have the concept of a mathematical graph in there, and once you have that, then that product or other products can do the job that you want it to do. So it's become easier actually to get this, because the people making this software now envisaged that you might be trying to do this, whereas before this they hadn't even thought that you could do this kind of thing. So the ArcGIS people have a lot of examples, even in their conference, of people doing sort of transportation related stuff, which they didn't have back then. Yes. Yeah. Well, I mean, in the case of our university, a site license for that product, which is mainly used by people in planning and people in geography departments, but there is a public domain QGIS, which is a public domain GIS, so you could do it with that open source software. Now, that's maturing in recent times. So, I mean, even a few years ago, it probably hadn't got the necessary capability, but probably it's much closer to that now. As to whether it's all the way there, that's tell you next year. We'll try and use it for something, but it's, and the other issue was, of course, that the capacity of computers, I mean, the reason why this GIS was a little bit slower to develop was because it needs a powerful machine. You can't actually have a map which has a lot of detail on it on the 1980s, PC, but it works perfectly well on a 2016 based machine of any sort. So the technology has caught up, and the data has caught up. So it's up to the modelers now to think of some way of using it. That's us.